I'm going to help you do a few examples where we are simplifying radicals, because sometimes our square roots or cube roots don't often end up being perfect whole numbers. For example, there is no whole number that multiplies twice to help me get 27, but what I can still do is I can simplify this square root. What we can do is we can think about what factors help us multiply to get 27, where one of them happens to be a perfect square. For example, if I take square root of 27, I can really say that this is the same thing as the square root of 9 times 3, because 9 times 3 is 27. And then we know that the square root of 9 is really 3, and then I have that 3 that's inside still. Okay? Another example is the square root of 8. I can figure out what multiplies to 8, where there happens to be one of them a perfect square. For example, 4 times 2, because we know then that the square root of 4 is 2, and then I have this other 2 that's still inside. So the square root of 8 is the same thing as 2 times the square root of 2. Another one is the square root of 180. We've got to figure out what two numbers multiplies to give us 180, where one of them happens to be a perfect square. Might be a little bit harder to think about, but how about 9 times 20? We know the square root of 9 is 3, and then we have a 20 left inside. But I'm thinking about something. I think I can take this 20 and I can break it down even farther. And that's what we always want to try to do, is we're going to break these down into prime factors if at all possible. So instead of calling this 20, could I say that this is really 9 times 4 times 5? There's where my 20 is. Because now I know the square root of 9 is 3. I can take that out. The square root of 4 is 2. I can take that out. And now I just have the 5 that's left in 5 that can't be broken down any farther. So the square root of 180 is really the same thing as 6 times the square root of 5. Okay? Another way of simplifying radicals, because sometimes it's a little bit harder to think about what perfect squares help me multiply to get the number that's inside, is we can break it down using a prime factorization tree. We can take this square root of 48 and break it down into a whole bunch of prime factors, meaning numbers that are only divisible by itself in 1. For example, if I have the square root of 48, I can break 48 down into 4 and 12. I can take that 4 and break them down again into 2 and 2. I can take the 12 and break it down, figure out what multiplies to 12, 2 and 6. I can break the 6 down into 2 and 3. So now I'm left with just prime factors. Once I have my prime factors, I can look for groups of 2. Because if I have 2 times 2, that's 4, and then we know the square root of 4 is 2, so that can come out. I've got another group of 2's, pair of 2's, 2 times 2 is 4, the square root of 4 is 2, so that could also come out. And then I have this lonely 3 that doesn't have a pair where he stays inside that square root. So the square root of 48 is the same thing as 4 times the square root of 3, using a prime factorization tree. Another example would be the square root of 72. Might be hard to figure out what perfect square multiplies to give me 72. So let's try to break this down into prime factors. I notice that 72 is an even number. It ends in 0, 2, 4, 6, 8. So I know it's at least divisible by 2. So I know 2 goes into there 36 times. I can then take 36, it's also even, so I can divide it by 2. 2 and 18. I can take 18 and divide that into 2 and 9, and then 9 breaks down into 3 and 3. So I'm down to my prime factors. I have a square root, so I'm looking for groups of 2. 2 times 2 is 4. Square root of 4 is 2. I've got 3 times 3, which is 9. We know that the square root of 9 is 3. And then I have this lonely 2 that's still left inside my square root. So the square root of 72 can be broken down into 6 times the square root of 2. Okay, here's another one. We have the cube root of 96. Now this is a little bit different because he's a cube root. So now we're looking for what number multiplies 3 times to give me 96. Okay, if there isn't a whole number that works, we can still use our prime factorization tree. And now we're just looking for groups of 3 instead of groups of 2. So let's break down 96. I notice that 3 goes into there 32 times. I can break down my 32 into 2 and 16. 16 breaks down into 4 and 4, and then I broke down my 4's into a whole bunch of 2's. All right, so now that I have my prime factors, I'm now looking for groups of 3. Because we have this group of 3, I have 2 times 2 times 2, which is 8, and then the cube root of 8 is 2, so that can come out. I don't have another group of 3 though, so this 3 stays inside, this 2 stays inside, and this 2 also stays underneath that cube root and multiplies together. So 2 times 2 is 4, 4 times 3 is 12, and so that 12 is still underneath that cube root. Don't forget about that little 3 there, because he's still a cube root. He doesn't turn into a square root, so be careful with that. So the cube root of 96 is the same thing as 2 times the cube root of 12. I hope that helps.